let's compare this bar magnet to electrostatics, because we're really good at electrostatics. Let's think about something called an electric dipole. So if we have a charge here, a positive charge, and we connect it to some negative charge with a little stick, an imaginary stick that keeps them separated, that's a dipole. It has two poles, a positive pole and a negative pole. And let's imagine this one is fixed. Okay. Now let's have another dipole here. Let's let this one have its positive charge like that, and its negative charge like that, and let's put it on a pivot. Okay. So it can't translate, but it can spin, it can rotate. So what would this thing do? Let's see. So it would feel a repulsive force here, do those two positive charges. It'd feel an attractive force here. So the net force would be down. Together, those would want to push the positive charge down. And then the negative force, the negative charge would feel a force that way, and it'd feel an attractive force that way. The net force would be up. Okay? So the negative charge would feel a force up. And it's on a pivot point, it's feeling a torque. So it can turn around this point, it's fixed there, and rotate. So what it's going to do in the end is it's going to align negative here, positive there on its little pivot point. That's what electric dipoles like to do. This is the lowest energy state, is what you'd say. So what we just saw was the same thing for magnetic dipoles. Okay, magnetic dipoles, if we have north here and south there, we just said they like to align like this. We have south here and north here. So it's basically the same thing. Now, it would seem then, if in electrostatics we can separate these and have different charges, that in magnetic fields, if we wanted to figure out the equations that are going to lead to this, we should be able to just cut these in half and then have north charges and south charges. That'd be what's called a magnetic monopole. If all the magnetic effects are contained just in one pole, and this is a free particle, then you have essentially a magnetic charge. Problem is, no one's ever found one. Some physical theories predict they should exist, but they never seem to show up. With this bar magnet, you'd say, well, we just got one, we cut it in half. But that's not what happens. If you take a bar magnet and you cut it in half, north here, south here, cut it in half, and you get north there, south there. And you cut it in half again, you make a little teeny one, you get north here and south there. And you cut it in half again, you get one like this big, north, south. You can never separate the north and the south. They're inherently mixed together. So when we start to tie this to electric fields, maybe we'll be able to see the reason why.